else we got? Now I want you to try some. And I will, yeah, okay, so here's one. Make a free body diagram of your calculator. So we have your calculator here, right? And you're going to set it on on your desk, and you're going to slide it across the desk. Okay? Calculators, you slide it across the desk, and it's sliding at constant speed. So what I want you to do is pause the video here, get out some scratch paper, and try to make a free body diagram of this, your calculator as you slide it across your desk at constant speed. When you're so pause the video. When you're done, start it up again, and I'll show you the diagram on my notepad. Okay, here we go. 3, 2, 1. Switching over here. So here's the calculator. It has its weight. It has the normal force, F sub n. It has you pushing on it, so F sub push. Some way to label it is the force of you pushing on it. And holding the thing back is F sub Fk, meaning force of kinetic friction. So we have a subscript and another subscript here. That's how we label it. The labeling is what it is. But the length of the friction vector needs to be the same length as the length of the pushing vector, because we're pushing it at constant speed. And if one of these was longer than the other, then the thing would either be speeding up or slowing down, because we need to have net force in this case equal to 0, because the calculator is in equilibrium. It is moving at constant speed, which means all the forces have to be balanced on it. Okay, so that's for the calculator that is being pushed at constant speed. Next one. Let's go to calculators. You slide it across your desk and it's speeding up. Okay, I've kind of given you a hint on this one already, and I'm going to slide right over to the diagram here in 3, 2, 1. All right. If the calculator is speeding up, that means that your pushing force is greater than the frictional force. So this vector will be longer than the friction force. That means that the net force is that way a little bit, and you want to try to make the net force vector basically equal to the difference between the push and the friction. So the net force is to the right in this case, which means that the calculator will be accelerating, speeding up to the right. Because remember, from second law, acceleration is in the direction of the net force. All right, next one. We want to make a free body diagram of a push broom as you sweep up some dirt. And I've learned that some people don't know what I mean by a push broom. So we're talking about one of these brooms that has the kind of the T-shaped thing and the bristles pointing straight down, and you push it along the ground to sweep stuff up. Now notice that this guy is pushing it at an angle into the ground. He's pushing it into the ground at an angle. And yes, as a result of that, the broom is sliding across the surface. But you have to push it down into the ground a little bit to get the dirt and stuff up out of the little cracks and grooves and nooks and crannies in the cement. So there is he's actually pushing it downward at an angle here in the direction that the handle is pointing, more or less. Okay, so make a free body diagram of that. Pause the video while you do it, and then you can see mine. So here I'm switching over to the clipboard. So this is for the push broom. That is the push broom. But the object we are interested in is the broom itself. Okay. Now there's a little bit of weight for the broom, F sub G, because it weighs a little bit. And then as you push it, you're applying a much greater force. So I'm going to call this the force of the push. Now, the broom is not sinking into the ground, so that means that there has to be a normal force, F sub n, which is equal to the downward component of the push plus the weight of the broom itself. So this normal force should be this length plus this length. I think I need to make it a little bit longer, but that's okay. And then finally, we're assuming we're pushing the broom along, we'll say at constant speed, so that means there's some friction here too. and the friction is the same as the horizontal component of the push. So this is F sub Fk, kinetic force, kinetic friction, I mean, kinetic friction. Okay? And if the broom is at constant speed, then the F net equals 0. If you are envisioning the time when the broom is actually speeding up and pushing the broom to the side, well, then you've made this vector a little bit longer, or maybe the friction a little bit shorter, and you're going to wind up with an F net of going that way. And that just depends on what moment you chose. Was the broom speeding up, or was it going at constant speed, or maybe even slowing down? Okay, that's it. The main thing I want you to get in this is that you can have forces that are acting not up and down and not side to side, but the vectors that are supporting them have to be able to cancel the vertical and horizontal components if the thing is in equilibrium in the stable configuration. Okay, let's go to this one. What else have we got? How about a car pulling away from a stop sign? So you have been stopped, you stepped on the gas, and now the car is starting to move forward. It's accelerating forward. What would the free body diagram look like for that? So pause the video, do your best on this one, and we'll flip over to the start it up once you've got a best guess. Okay, so here we are. So we have a car, and there is a significant weight to the car, F sub G, and there's a significant normal force supporting the car because it's not sinking into the ground or flying up in the air. And there is a sideways force which is causing the car to accelerate to our right in this case. Now the question is, what is that force? Okay, and the answer is it's actually friction. It's a force of static friction between the tires and the road because the engine is trying to make the wheels turn, but they're stuck against the ground. So the wheels are trying to push the ground backwards, and the ground in return is pushing the wheel forward because of the static friction. Now we're going to learn more about this next time when we talk about Newton's third law, but yeah, as weird as it sounds, it's the friction of the road pushing the car forward that makes the car go forward. Now, why is it static friction? Why is it static friction? It's because the car is, the wheel is not, let's do it this way. The tire is not sliding when it rolls. If you take it will make a nice, neat tire print because it's as if it pushed down and came right back up again as it rolls by. It's not sliding along. When the car is rolling, there's no sliding between the surface of the tire and the surface of the road. So it is static friction. Now, this actually is relevant to you because when you slam on the brakes and you start to skid, now you've changed over to sliding friction, to kinetic friction. And kinetic friction, as you know, is weaker than static friction. So when you lock up the brakes and you start to skid, the brakes don't work as well. And you're going to go farther than you would if you kept the brakes from locking up. Okay, so it's a good thing if you can keep your presence of mind if you are starting to skid your car. If your wheels have locked up and you're sliding along, you need to ease off on the brakes a little bit to regain that contact with the road to stop the sliding, and then come back on with the brakes again, but not quite as strong, so that you're right at the threshold of skidding, and that's your best performance. That's your best braking. Okay, last one. Question is, what about a free body diagram of your car as you're going around a curve at constant speed? So this is going to be a centripetal acceleration, which we've talked about before. And I'm just going to jump right back to the, you guys can try to make one here, but here we are. Okay, for the car with going around a curve at constant speed, it actually looks exactly like this one. This is the car pulling away from the stop sign. It's exactly the same diagram. It's just that you have to be aware that when the car was moving away from the stop sign, the car was moving to our right. When the car is going around a curve, we have to know that the car is going toward us or away from us. And then there is a frictional force between the tires of the road, which is pointing toward the middle of the curve, toward the center of the curve. But oddly enough, the free body diagram looks exactly the same. It's just the direction of the motion of the vehicle that is different. And we don't show that in the force diagram or a free body diagram because this is only forces. It's not velocities or anything like that. So, yeah, this is the same diagram for a car going around a curve. Okay, that's enough examples to get you going. You're going to have plenty of these to do in your homework. I think you'll agree once you get used to them, you can do these really fast. You can write them much faster than I did because you don't have to be talking so much. The important points are that all forces are accounted for and all forces are labeled, and you can use the diagram to calculate or estimate the net force acting on the object, because that's why we make free body diagrams, is to be able to visualize or approximate net force. All right, thanks for your time, and we will see you next time.